faced in terms of an academic, but problems that have come to me from companies that were facing some of these issues. So I'm going to speak about two different applications, one with linear optimization, the other with nonlinear optimization. And both of them have to do with problems in the electricity sector. And this is joint work with various people that I've collaborated with, and in particular I'll mention the two students that worked a lot on these problems, Thibaut Barbier and Guillermo Bautista. Guillermo is now a senior market analyst at the California ISO, and he worked on the optimization application to the electricity markets problem. And Thibaut is now an intern at Expressio, which is a spin-off company in Montreal. And he worked on the application to design electricity supply for remote sites. And those are the two problems that I'm going to speak about. So here's the outline. I'm going to speak about these problems for as long as I can go within half an hour and then conclude. So as I mentioned, the first problem is really looking at equilibrium in electricity markets. And the idea here is, this is joint work with Guillermo and Tony Vanelli. And the idea here is that if you run an electricity market, the network plays a very important role. Because the network, because electricity doesn't flow the way you necessarily want it to flow. The electricity flows the way Kirchhoff's laws tell it to flow. And so there may be ways for certain players in an electricity market to influence the outcome by taking certain actions, such as supplying more or less power, or providing or assigning certain bilateral contracts that will bias how the system behaves. So the question is, can we actually build a model that's going to permit us to understand how these various behaviors can impact what the market does? Okay. Having this ability to influence the market is what's called market power. And the idea is that the transmission system is particularly important. And one of the limitations for most models that look at these market issues is that they use linear approximations of the power system. Okay. So what we did in this work is to actually work directly with the AC description of the power system, which is, from an optimization perspective, hard because it is in particular nonlinear and non-convex. The nonlinear part, one can actually write this in a polynomial form, which is what we used. I'm going to skim very quickly over that, but that'll come out later as well in the talk by Jakub that will speak about optimal power flows, and the same equations will show up. So that one actually has a nice connection to polynomial optimization. So what we look at is what we call a multi-leader single follower game for the market. And we formulate it using nonlinear optimization, and then we can get results that really show how different the outcome from a market can be, whether you solve it using a linear approximation or not. Okay. That's basically what I'm going to show. Here's the idea of our market model. What we have here is a certain number of generating companies, or GenCos, that are competing against one another. But they are the ones that are deemed to be large enough that they have the potential to influence the market. So these are the guys that we want to observe, to keep an eye on from the point of view of the regulator. Okay? Someone like the ISO. And then down here we have a follower. So these guys are the leaders of the game. And here we have a follower where we have the ISO that observes what's going on and clears the market. We have all the various demands in the market, which here are assumed to all be small enough that they won't actually gain the market. And we have all the other suppliers that will simply take whatever price the market gives them. That's what we call the competitive fringe. So these guys we can basically all lump into one follower, and these large generators here are the ones whose decisions will impact the outcome. I'm going to briefly show what the difference is between modeling with a linear or nonlinear equations. So if we look at the DC approximation for the transmission system, we have a linear equation on the phase angles here. So theta is the unknown. If we look at the detailed transmission system, we have two equations. We have this equation here, which is the detailed version of this one. Okay. So here we've basically said the cosine is small enough, and we approximate it with the angle. And the voltages are all approximately 1, so we simplify things and we get that. Okay. And then there's this other equation that completely disappears, which is the reactive power equation. So the difference is we're going to use these equations instead of this one in our model for how these various players interact through the network in an electricity market. Okay. So this is the first set of differences. The second set of differences is this one, where here's a detailed description of the transmission system again, and this is the simplified version for those equations. Again, here we have the magnitude of active and reactive power, and here we have a simplified version of it. And then we have here also the generation modeling, where the simple version is that the power generated is non-negative, whereas the more detailed version actually looks at the curve here for a generator and does a more detailed approximation of what this curve looks like. Okay. This is basically a curve that describes, without getting into too much of the technicalities, it describes the levels at which a generator can actually operate. Okay. There's technical limits on what can be done. I'll show you results for using these models on this model on a very simple system. So here's a 3-node system. So we have node 1, node 2, node 3, and 3 lines that connect them, a triangular system. We have generation at node 1 and node 2, and we have demand at node 2 and node 3. Okay? And we put some limits on the voltage. The demand, the price reacts to the demand. So if the price goes up, demand goes down. Okay? So we assume that the demand is price reactive. And we have some technical limitations on some reactive demand at every node for the stability of the system. And we have here an equation that gives the cost. So also, as generation increases, the cost of generation increases. The amount generated increases, the cost of generation increases as well. And it's usual to model this using a quadratic function.
But that's DC economies of scale.
This is not quite, it's actually the opposite. I mean, the marginal cost of generation increases with each unit.
Yeah.
So if you're generating more, giving an extra unit is more expensive. So this is actually a convex quadratic that's increasing. Okay. And here the price versus demand, we assume that it's a linear function. Okay. This is some of the data. I won't really go through all the details, but it's basically putting the data on the 2 generators, G1 and G2. And here's the outcome if I set up the large nonlinear optimization problem, which I didn't show because it takes a while to work through the whole problem. But we're basically looking at a bi-level optimization problem on that market. And here's the outcome if you solve the DC model. So we have generation amounts for G1 and G2. These are in megawatts, okay? And then we have power flows of 40 this way, 318 this way, and 358 this way. This is what's drawn by the demands of the 3 nodes. And one of the things you get with a DC model is that there's a single price for electricity for the whole network. Okay? And in this case, it's going to be $57 per megawatt hour for the energy. Okay? So what I've done here is taken this problem, okay, and set up an optimization problem that says I want to maximize the profit for these guys, subject to having an equilibrium in the market with the followers here and their decisions as a leader. Okay. So it's a bi-level optimization problem. Write the optimality conditions. Make sure that the power flows all satisfy the simplified conditions at the top, this one, and this one. Okay. And you solve. And then from the dual variables at each node, you get these prices. Okay. But in the linearized model, the dual variable is the same at every node. So you just get the same price no matter where you are in the network. Okay. The interesting part is if we now use the full model for the network, here's one solution that we get as a market outcome, as an equilibrium. We now have different prices at each node. Okay. So it turns out that 1 megawatt hour at node 3 is actually worth more than at node 2 or at node 1. Okay. And this has to do with the fact that there's going to be limits on how much energy, how much electricity we can get to node 3 because of the way the network functions. Okay. So it's actually more valuable to have generation here than it is there or there. Okay. In fact, there is no generation here. Right. So this is telling me if I was going to open a generator, I'd be more interested in putting it here because this is where the value of electricity is the highest in the market at the moment. So this is one of the phenomena that we see. The other thing that we get is we also get reactive power flows, which are the numbers at the bottom here, which we don't get with this linearized model. And this is because we've totally omitted the equations for reactive power flows. Whereas here we actually see what's happening in terms of the reactive power flows from one node to the other. Another aspect that also gets modeled is the losses. If you notice on each edge, instead of having a single number of megawatts, I actually have two numbers. I have active power on top and reactive power at the bottom, and there's a loss going from 1 to 2. So the amount injected is 99, but the amount that actually arrives at node 2 is 96. And this is much closer to the behavior of a real electricity network. So in short, we get a lot more information out of one of these solutions than from one of these solutions.
And the assumption that all demand loads are purely resistive.
Yes, yes. So this is why I had some of these details back here, but that's correct. Yes. Another interesting aspect of this is that in the nonlinear model, in general, the equilibrium is not unique. So your market might land, instead of this solution, at this solution, where the prices have now changed. Okay. So here it's gone from 59 to 61. Here it's also gone up, and here it's also gone up. We still have the same general pattern that power is more expensive at node 3 than 1 or 2. But it is a different equilibrium that could be reached by the market. Okay. And the power flows themselves are also going to be different. So for example, in particular, instead of having nearly 100 megawatts going from 1 to 2, I only have 67. And in fact, it's flowing from 2 to 1. So it's a very different solution in terms of that qualitative aspect of it. So the key difference really is how detailed do you make the description of the network, leaving all other assumptions the same for both the linear and the nonlinear model. The advantage of this is that we can really look at what happens in terms of strategic behavior. If the model can predict these kinds of results, you can start simulating things like, let's suppose the generator 1 is not quite following the rules. What would the possible outcomes look like? And then if you observe those in reality, then you have some evidence that allows you to argue that generator 1 is cheating. It's very hard to prove that generator 1 is cheating and not following the rules. But this kind of detailed model can actually allow the ISO to have some evidence, to accumulate some evidence of possible market power. And the key thing is here is that you really have to use nonlinear optimization to do this. One important point as well is that this approach is computationally effective. This is an example on 3 nodes. This runs fairly fast. But we have run also examples with much larger networks from the IEEE standard benchmarks for the purposes of publishing. And you can get these results in reasonable time. You can run a lot of simulations in a day to get a sense of what's going on. So this is computationally effective. And then this can also be used for different kinds of equilibria. So the equilibrium that I discussed here, without getting into too much detail, is what's called a Nash equilibrium, that's from a what's called a Cournot-Stackelberg game. You can change the rules and apply the same principle to find different kinds of equilibria as well. Okay. So the point really is that it pays off to have the more complicated model for the network, and it can be solved using the tools that we now have from nonlinear optimization. Okay. So that's the first part that I wanted to mention. The second part that I want to mention is a different problem, which is the problem of designing a system to provide electricity in a remote area. Okay. And this is joint work, as I said, with our student Thibault Barbier and Gilles Savard from Polytechnique, Montréal. This is important in Quebec because we have a fair amount of activity that takes place in the north of the province. So we have the United States down here. North of the United States, there's a country called Canada. Within Canada, there's a province called Quebec, which is this red piece over here. And then far up in the north, of course, most of the population lives down here. Far up in the north, it looks like this. This is Newfoundland and Labrador here. And there's actually, for example, a mine at 62 degrees latitude, somewhere up here, called the Raglan mine, that exploits nickel. Okay. And if you wanted to connect the operations of the mine to the network, you'd have to draw a line from up here all the way to down where this water is. This is where there's a large chain of dams called the James Bay Complex that generates a very large amount of electricity. And that's nice, but it's a long way to go. So if you wanted to do this, it would get very expensive. And the idea is to have, of course, an autonomous system there to provide the power for the mine. So the mine has an expected lifetime. So we want to plan what equipment do we place to provide the mine with power for this expected lifetime. Okay. Traditionally, what one would do is to put some generators, so there's some load to provide. We put some diesel generators, we figure out how many we need to put, and then we fly in, actually we boat in, because flying would be very expensive in this case, the fuel for the generators to provide the load. A more recent approach is to say, well, maybe we can have wind generation as well. If it's a location where there's enough wind, we can think about putting up some wind turbines and using that to save on the cost of fuel for the generator. Okay. Now we have some decisions to make in terms of balancing these two, right? So we need some kind of control system that's going to be installed that's going to make decisions about how much to run the generators and how to operate the wind turbine as well. Okay. So this gets a little bit more complicated. The next ingredient is to actually take advantage of the fact that we now have reasonably good batteries that can be placed on site. And now there's this idea, conceptually, that if your wind at some point is enough to provide the demand and more, then we take the more and we put it in the battery. And when we don't have enough, instead of running the generator, we could draw from the battery to supply demand. The point is to try to save on fuel, because that's the expensive part on the ongoing basis. Okay? So now the control gets even more complicated. There's also the fact that here there's going to be loss from the battery, and there's going to be also some loss because there's a conversion from DC to AC that has to take place when you do this operation. If we now take this idea and we say, okay, we want to design a system like this for one of these mines, well, we have to decide first how many of these generators, how many of these windmills and how many of these batteries do we put. This is a capital investment up front for the sake of operating the mine. So that's the first decision. The other part of the decision is we have to design this control system that actually operates them. And the objective there is to do it in such a way that we minimize the use of the generators and the cost of diesel. So there's two different optimizations going on, the upfront cost and the running cost for the years that the mine is going to be operating. There is actually such a setup in existence, at least one. There's an example in Alaska, in this place called Kotzebue, which has 11, almost 12 megawatts of diesel generation, a battery of almost 3 megawatt hours, and a wind turbine that can reach up to 3 megawatts of generation as well. Okay. So this is really done in practice. This is one such example. And this is an example of how these control strategies work. So they'll say something like, is the wind power more than the load? If yes, then use the wind and charge the rest to the battery. If no, then I look at the state of charge of the battery. If the battery is fairly high, more than 50%, I'm going to use wind and use the battery for the rest. If the battery is low, then I look at the actual demand. And depending on the level of demand, I either use wind plus the generator and charge the battery to increase this percentage. Or if the demand is really high, I have to forego recharging the battery and just put the generator towards demand. This is a simple example of such a control. Okay.
Miguel, does the control ever play with smoothing the demand? Because that's something you could...
That's a good question. As far as this model is concerned, we didn't handle smoothing demand. We just assumed the demand is there, we have to supply it. But a next step would be to actually do what's called demand response, which is to manage demand to smooth the load. We haven't done that. But in principle, you could do it because you got full control. It's your mind, you're setting up the system. So that's a good point. We haven't put it in this model. But in principle, it could be done. Yeah. And then then it would simplify some of these decisions, but it would complicate because now you've got to put the demand response decisions into here, right? And they might involve decisions about stopping operations, which might or might not satisfy the managers, but that's a different question. That's a good point. Yeah. So we're not doing that.
How often will be the decision revised or changed?
This decision of how much equipment you put would be typically one and done.
No, but
Sorry.
control.
Oh, the control. The control is also usually one and done. So you set up the system and you design the control, which is hardwire that goes into the system.
Then you have to decide, dependent on the state of the system. How often is this decision made?
Well, the state of the system is in these decisions here, right? Because the system is fixed, and we know, we have we assume we know what the demand is going to be like. We can design the system once, and that's it. It doesn't mean we couldn't revisit it and optimize later, but the approach here, and I'll get back to that in a moment actually. If you just hold the question, I think I'll say more about that in a moment. So this is the kind of decisions, this kind of situations that one would have. So at some point, for example, in the first hour, there would be a load of 100, 60 coming from wind, 60 from generation, and then 20 going into the battery. Next hour, the load has dropped, and maybe there's a lot of wind, so we stop generation and we run 10 into the battery. And then here we actually have to discharge the battery to make up the difference and still avoid generation. Okay. So we have a pattern like this for what's going to be happening at each hour. There's a software that's been designed by the US Department of Energy to do this kind of analysis. It's a piece of software called Homer, and the way it works is that it fixes the strategy and then simulates all the possible designs. Okay. So the way this works is that it has decided what this strategy looks like. That's actually fixed. Okay. And now we decide, given this strategy, how do we make these decisions on the equipment? Okay. And it just runs a lot of simulations based on demand forecasts and wind forecasts to figure out how much equipment one should buy. So from Homer's perspective, the strategy is fixed, and we just try a lot of design combinations for the equipment, given some data, and then we just pick the one that gives the minimum cost. Okay. From our perspective, there's some limitations with this approach. One of them is that the strategy is influencing the design, which is, in a sense, not necessarily the way it should go, when in fact the strategy probably should depend on the design as well. You have to do the strategy depending on the resources you have. And then the other aspect also is that really the strategy should be site dependent. Right? The amount of wind you get is going to vary from site to site. So why should the same strategy always be the same? Why should the same strategy always be the right one, so to speak? Okay. So the proposed approach is different in that we do the following. We have no strategy. We set up a mixed integer linear optimization problem that's going to define both the design, so what equipment do we install on the site, and the optimal dispatch. So given the forecast, it's going to actually have a strategy that for every single hour for the period of forecasting is going to tell you what the dispatch should be. So it's the ultimate strategy. It's extremely detailed for your current forecast. Okay? So we really get an optimal dispatch without a strategy per se, but of course in practice we need a strategy, so from this optimal dispatch we can then apply data mining techniques and come up with a reasonable strategy that's actually implementable in practice. So let me just quickly again scan through the model. We have the sets of equipment and the hourly data. And what we want to do is minimize the cost of setting up the system. So this is the initial upfront cost. We want to make this as cheap as possible, subject to being able to provide the load and satisfying all the power constraints and the cost constraints, which you can imagine the kinds of constraints that have to be satisfied there. There's nothing particularly mysterious. So with a particular scenario, we can run our model and we can run Homer. And the outcome is that for the project cost, so this is the initial upfront, here's how much equipment you have to put in, we get a 5.3% reduction with respect to Homer. And then this is the differences of how these things run and how, actually, no, I'm sorry. This project cost also includes, this project cost also includes the cost of running it for the life of the mine. Okay. And in particular, here's the cost of the for the wind, the generation, and the batteries. And if you look at the dispatch strategy, this is what it looks like. So we have a very, very detailed strategy that takes into account a lot of small variations. So of course, this is not usable in practice. But what we can do now is look for a better strategy. Of course, the moment we have a better simpler strategy, the cost is going to go up. Okay, because we're not going to be quite as refined. So the question is, can we still have a cost savings compared to the Homer approach? And basically what we do is we take the data, we apply a very straightforward data mining approach. We take this optimal dispatch and we try to extract rules that reproduce as much as possible the decisions that were made before. So we want to find a set of rules that minimize the difference between the optimal dispatch and the dispatch that we get from this particular tree that we extract. Nothing very sophisticated. And we come up with this final decision tree, which is a lot simpler. So you can see that it has to do with the ratio of wind over demand, the state of charge of the battery, and then all the various levels to make the decisions. And of course, the cost goes up because the operation is not quite as optimal, shall we say. But we still are able to pull some cost savings compared with the cost from Homer.
Excuse me?
Yes?
Is the strategy more complex than in the Homer case?
Yes. Yes, I believe so.
Could you have the same constraint as in the Homer case and have a saving?
If we put the same strategy as the Homer case, in principle, we reproduce this.
But not the
solution.
same strategy, but the same number of decisions. Basically.
Oh, the equipment.
The same number of branch in your tree.
Sorry. Yeah, so what's the question about the...
So in your Homer strategy, you have,
Yeah.
I guess, a number of decisions at each level.
Right.
So if you count the number of decisions,
Oh, if you
And
count
you-
the size of the tree.
yeah, basically, yes.
I'm not sure off the top of my head. I would have to check.
Because this would be the right thing to compare, right?
In terms of the actual implementation of the... That's a good point. I don't know off the top of my head. That's a good question. I know it's different, but I can't tell you immediately how different... I mean, from that measure, how different it is. That's a good point. Yeah. But it is definitely different because we still get some nice savings out of that. So basically, the idea is the summary is that with this approach, the philosophy is to say, forget the strategy, do an optimal design and an optimal dispatch using linear integer optimization, get the design and the optimal dispatch, then from that start compromising by simplifying the strategy to eventually get something that you're happy with. Okay. One of the nice things I find about this approach is that in a sense we have here a bound on how good you can be regardless of which strategy you pick. And now you have an idea, if you pick a particular strategy, here's how much it's costing you in a sense compared to this optimal strategy, which is a utopia in a sense. So there is some I would argue some very nice information, useful information coming out of this approach by really looking at the optimal dispatch and not constraining the dispatch from the start. With respect to Homer, what in this particular scenario that I showed, as I said, we get a savings of at least 1.6% and also 10% of fuel consumption reduction per year. So it's a significant cost as well when you've got to get fuel to these remote places. And to conclude, I've put here some references on the first part of the work. The second part of the work is very recent, and the papers are in preparation, but I'll be happy to send the information to you if you're interested once the papers are available. And otherwise, I'm willing to answer any questions that you may have later this afternoon or whenever. And I've put here my email address. Thank you for your attention.
Thanks, Miguel. So as I said before, just one or two questions, please. That's if anybody has any.
Yeah, don't you
Yes.
consider unit commitment constraints where, if you consider maybe you don't want to use all the wind power even if you can?
Yes. Well, basically, this is like a unit commitment, right? I mean, it's a very simple unit commitment problem. You've got these resources, and you manage them, and you have to decide which way it goes. So in a sense, this is the answer to the unit commitment.
Okay, but when
Right.
we have the wind power, you use it all. You don't.
Not necessarily. Not necessarily. No. It depends on how these decisions go, right? You may find it more economical to not, if your generator's not running and your battery is full, then you just supply the load and you have enough wind for the load, then you just supply the load and you basically, dispose of the remaining wind because there's nothing else you can do with it. So you can't do wind commitment in that sense because you're isolated, right? You have nowhere else to send the extra energy. It's probably an unlikely scenario, but in that sense, it's like a mini unit commitment. So I'm not convinced that thinking about it as a unit commitment necessarily makes sense. But we can talk more about that.
it would make more sense to think about it as unit commitment if there were some strict operational constraints. For instance, in thermal generation, you have to put the turbine on for a certain amount of time, or
Yes.
keep it off for a certain amount of time. Whereas with the diesel generators and wind, you very likely have relatively few of such operational constraints, and you can really put things on and off at will.
But there's a price to put it on and off, so maybe it compensates to save the wind on the battery.
Not so much in this case. I mean, we basically assume that these guys are more or less, turn on and off at will. Maybe there is some cost, but it's not the same as with as Jakob was saying, with some thermal generations where you really have constraints on turning on and off. Or the ultimate one would be something like a nuclear plant where you're stuck. You have to operate with this level, and you have to make do with it.
Okay, thanks very much again.
Thank you.